Okay, welcome back. And here we are at the first lecture of the Environmental Bioethics course for the summer. Okay, so thank you once again for coming in anticipation on this day. And we'll begin, as always, in the name of the Father, the Son, and the Holy Spirit. Blessed Trinity, we love you, we adore you, and we thank you once again for all your many blessings, for the gift of life, and for having us here. We ask that you continue to be with us as we explore the wonders of your creation, especially from the bioethical perspective, as now we engage in this course on environmental bioethics of the present issues that we have today with regards to climate change and global warming and just the good old contamination of the earth from pollution, even outside of the issue of climate change. There are many, many issues that we need to deal with as we seek to care for the creation that you have given to us, Lord, to be good stewards as you expect from each one of us. As always, we pray in a very special way for those who are in most need of your divine mercy. In the name of Christ, our Lord. Amen. Father, Son, Holy Spirit. Okay, I always ask at the beginning if there are any questions or comments from previous lectures or events, anything?
I have a question, but
yes?
we'll do it after
sure.
the problem.
Okay, no problem. All right, so today we're going to start the course on environmental bioethics. And it will cover several different aspects. We'll have, I think it's a total of 7 lectures altogether. And I'm going to start kind of at the end of this presentation here, where it has the biosphere. This is the planet Earth on which we live, and this is an actual photograph. It's a satellite photograph of the Earth, or maybe from the moon, I don't know. But it's a photograph. So we can see a lot of activity here, not only the oceans and the continents, but also the weather activity in different parts of the world, with the swirls and circles as weather patterns are forming. So it's a very dynamic system. When we look at the Earth from a physical aspect, and also life on Earth, all organic life, not just human, but non-human life, we can subdivide it into 3 areas, 3 main areas, whether it's solid, liquid, or gas, basically. Okay, so we have the lithosphere, which is a reference to rock, it's either Greek or Latin, I forget, but lithos is a rock. So the lithosphere is a reference to the dry land, to the continents, basically, where we live, okay? To the dry land and all the plants and animals and everything else that lives on the continents. The hydrosphere, of course, is a reference to the water, hydro, which includes mostly the oceans, but also lakes, rivers, streams, etc. Estuaries, okay? Hydrosphere. All kinds of animals and plants and bacteria live in that environment. Then there is the atmosphere, which is the gas portion, if you will, of the planet. There's some life that at least circulates through there, like birds and many other living creatures, pollen and etc. Right? The atmosphere is basically what keeps us alive because of oxygen and what is needed for life on Earth. So altogether, these 3 main areas or media in which to live, right? Whether it's land, water, or the atmosphere itself, these 3 together is what we call the ecosphere, because that's where life exists as we know it on this planet, organically speaking, okay? So I'm not talking about, again, the life of God, the life of the angels or the saints. We're talking about organic physiological life. So far, this is the only planet where we know life exists, so far, okay? So we're going to be studying, each lecture will be devoted to one of these regions. And then there'll be a lecture on energy and a lecture on pollution and human population growth and so forth. And some creative ideas of how to curb the contamination of the earth. Because like I think I said it before, we're the only species that actually produces waste that stays around for literally thousands of years, okay? No other species has that capacity. Usually they die and they disintegrate and they form part of the ecosystem and get recycled. But we produce these artifacts that now are capable of staying for a relatively long period of time, and we're beginning to see some of the negative effect of that in the ecosphere, affecting either life on Earth or life on land or life in the oceans and so forth. Okay, now I'm going to go back to the top, to the beginning. And this lecture today is devoted to the lithosphere, or the land. And we're going to get a little bit into geophysics, but these slides are kind of backwards. Before that is a review I have here on the universe and the origin of the universe, where we start. I'm going to pick up a little bit from when we left off in the first course on the program on fundamental principles in Catholic bioethics, and how we were integrating the physical reality that surrounds us with our beliefs, right? In other words, the evidence from science of origins, and integrated or complemented, if you will, with our beliefs that come to us in part from scripture, but also from the tradition of the church. In other words, the theological thinking of the church, like, for example, the theory of the Big Bang. And I think I talked a little bit about the Big Bang and the origin of the universe when we were talking about, in the first course, the fundamental of, principles in Catholic bioethics. I talked about three origins, right? The origin of the universe, the origin of life, and then the origin of humans as a species, not individually, but remember I call that phylogenetically, right? Phylogenetics, in other words, the origin of the whole group, in this case, the human species. And then in the course on the beginning of life, we looked at the origin of individual human life ontogenetically, ontos meaning the individual. We did that, which we landed at conception, at the process of fertilization, or the zygote. Okay, so let me go back then for a moment, just pick up very briefly the origin of the universe, which points to a creator in the sense that we start from nothing to the entire universe that we have today, this expanding universe, in about 14 billion years, 13.7, I think it is, or 13.8 billion years, all right? Remember that a billion, this is an American billion, meaning that it is 10 to the 9, and not the European billion, which is 10 to the 12. Okay, so this is 1,000 million years, whereas the European billion is a million years. But it's rather interesting that from our tiny little Earth here, okay, which we put in perspective, one of the other classes I'll put the size of the Earth in perspective to the size of the sun, all right, and then that is just one planetary system within a galaxy, our galaxy, which is called the Milky Way, which is one of millions of galaxies that exist in the universe. So the amount of matter, of material, is just bewildering to be able to understand it, right? To wrap our minds around that quantity that is so immense, exorbitantly immense. And even so, it's estimated that the matter of the universe is only about 4% of the entire universe, okay? A good quarter of the universe is what is known as dark matter that we can't see. For example, the center of black holes that are so dense that not even light gets to get out, all right? And even that is only about 1/4 of what truly comprises the universe as a single word or a single meaning, meaning everything that is, everything existed, because it's estimated that at least three quarters of the universe is dark energy. And dark energy, we really have no clue what it's about. But we have some intuition that it exists. Not we, I mean astrophysicists and so forth, people who really get into this science of astronomy and cosmology because of what is known as the background radiation. The background radiation, which is estimated to go back to the origin, so it goes back about 14 billion years ago. One more thing I want to say about that is first, it's a true origin in the sense that before the universe, that Big Bang, that explosion, that moment of singularity, there was nothing, all right? There was really nothing. So it is truly an act of creation. And here is where there is a possibility of integrating or complementing the knowledge of astronomy today, this 14 billion years, and to go just before that, nothing meaning there wasn't even time. There was no time either. All right, so also astronomers are telling us that in this 14 billion years, there have been two big moments, if you will, or two big categories, two big events. The first one is called expansion and then inflation, all right? Oh, sorry, inflation first and then expansion. And the order of magnitude is totally different because inflation, which is from the moment of singularity, the beginning of time and place, right, to the formation of the first subatomic particles and the subatomic particles. Let's go back for a moment to the atomic theory, which is still the standard in quantum mechanics. Still, the atomic theory, the classical atomic theory still holds in the sense that the basic unit of matter, of stable matter, is the atom. The atom is made up of subatomic particles, all right? So the atom is a stable unit of matter. Anything material, we can break it down and break it down and break it down till we get to molecules. And when we get to molecules, we can break molecules down to atoms. For example, water, all right? There's water inside this plastic thing, and there are gazillion molecules of water in there. But we could hypothetically isolate each one of those molecules, and we'll see that those molecules are made up of three atoms, right? The molecule of water. And what's the formula for water? The chemical formula? H2O. So the three atoms are two of hydrogen and one of oxygen, okay? Keep it simple. Those atoms is stable. In other words, this is not exploding. This is not radioactive, right? Those atoms are relatively stable. That would stay that way for a relatively long period of time, years, centuries, millennia. The individual molecule of water, because it has the stable atoms of hydrogen and oxygen. But it turns out that those atoms are made up also of what we call subatomic particles, all right? And the three classical subatomic particles, protons, neutrons, and electrons, all right? And they're classified that way according to their charge. And we know that the protons they have a positive charge, the electrons have a negative charge, and the neutrons, by definition, don't have an electrical charge. But they do have a mass, the neutrons. And the protons also have a mass. They weigh something, all right, as small as it is. So they tend to stick together, protons and neutrons, in the nucleus of the atom, whereas the electron orbits around the protons and the nucleus and the neutrons. And the mass is not that the electrons don't have a mass, but rather the physicists call the mass of the electron as a negligible mass. It's so tiny in mass, right, that it is negligible as far as their existence is concerned. So typically, physicists, when they talk about the electron, they actually talk about an electron cloud. And it gets into probability that where the electron is around on the shell of the atom depends on probability, depends on this cloud. All right, so all this to say that atoms are relatively stable. They're made up of subatomic particles, and the three classic subatomic particles are protons, electrons, and neutrons. And then there are other particles that have been discovered, like positrons and so forth, which would be kind of an electron, but with a positive charge instead of negative, and whatnot. But now they have also discovered a deeper layer, a smaller layer, if you will, which are generally called the quarks. And these are the ones that make up the protons, electrons, and neutrons, especially protons and neutrons. That category is called quarks. And there, when we go into that field, we're getting truly into what is known as quantum mechanics and so forth, and the theory of relativity. But these are known mostly statistically, but there are some experiments that have revealed their presence or their effect on what is known as the accelerators or the colliders that are in different parts of the world. There are some here in the States and some in Europe. Anyway, so we have now subatomic particles. Okay, we have subatomic particles, and those are the quarks, and those are the smallest particles that we have discovered yet, that scientists have discovered, and it's a number of them. What happens is, from the Big Bang forward, from that moment of singularity, an instant before which there was nothing, right? Within fractions of a second, the subatomic particles are formed. They coalesce, all right? So the hypothesis is that they themselves are formed by smaller fragments, which we have no clue about. But that's the hypothesis, that's the mathematical hypothesis. But they coalesce within fractions of a second. We're talking about 10 to the minus 20 seconds, all right? Which is, again, a bewildering, small amount, fraction of time that we can only comprehend mathematically, but I don't really comprehend it existentially, all right? I can barely comprehend a second. Like I say, well, 1001, 1002, 2003, those were 3 seconds. But when you start fractioning that into pieces, then it gets very weird. At any rate, that is the inflation part, okay? The inflation part is that within fractions of seconds, the subatomic particles form the quarks. That's what's illustrated by the first series of balls here. Oh, look at that, 10 to the minus 43. I don't know if you can see the time scale. 10 to the minus 43 seconds. All right, that's 43 orders of magnitude smaller than a second. In that temperature, in that time, the quarks were formed. And then a few nanoseconds later, the subatomic particles were formed, protons, neutrons, and electrons. And a few nanoseconds later, atoms were formed. So to get to atoms, all right, it took 10 to the minus 6, 1/1,000,000th of a second. 10 to the minus 6, that's a dot and 6 zeros, right? So it's 1/1,000,000th of a second from that's why it's a Big Bang. That's why the explosion, from nothing to all of the atoms that form the universe. All of the atoms that form, imagine all of the atoms that are forming just this, okay, or this computer. And then all the computers on Earth, all the desks on Earth, all the vegetation on Earth, all the humans on Earth, all the everything on Earth. And Earth is just one of the millions and millions and millions of planets that are out there. And galaxies and so forth. All of that was formed in 1/1,000,000th of a second at the atomic level. But they were loose atoms. And they were flying out at an incredible speed outward. So that's why it's called inflation, okay? This explosion is expanding, it's inflating. Time literally is inflating through. Until they get to the order of seconds and then minutes. And things start slowing down. And they start slowing down incredibly to the point that we jump from nanoseconds to minutes, and from minutes to thousands of years, and from thousands of years to millions of years. So the scale of the expansion of the universe, which is the second moment, the expansion is measured in millions of years, and hundreds of millions of years, and thousands and billions of years is the second moment, which is the expansion moment. So the inflation moment is measured in fractions of a second. 10 to the minus 20 seconds, 10 to the minus 40 seconds. All right, incredibly boom. And then the expansion, incredibly slow in compared to the inflation, but real, constant, and like the word says, expanding. So what do we experience 14 billion years later, standing on this earth and measuring out galaxies that today appear at this distance, and 3 years from now, which is a measurable time, appear at this distance, and then 3 more years, they're at this distance. That's telling us that they are going away from each other. They're expanding. And it's similar to a balloon, where we have a balloon small first, and we poke it with a marker, all right? And then we inflate the balloon, and those dots become further away from each other. Mm-hmm. You can do it three-dimensionally. I heard a talk one time on Einstein. You can use raisin bread and think that the raisins are the galaxies. And as the bread rises in the bread inside the oven, then three-dimensionally, those raisins are getting away from each other. All of them are getting away from each other, right? As the bread is rising. That's a very crude, tasty analogy of the expansion of the universe. Discovered by the Hubble telescope, named after this astrophysicist, Hubble, which for the first time was able to measure distances outside of the Earth's atmosphere because it was in orbit, you see? And so it got rid of the filter of the atmosphere, which makes things very fuzzy when you're trying to measure millions of light years away. By the way, I might as well throw in, since we're talking on such magnitude of scale, a light year, which is a measure not of time, but of distance. A light year. And a light year is defined by the distance that a photon, that a light particle travels in a year's time. And what is that distance? I'm not going to go through the calculation now. Maybe you, in a moment of boredom, you can do this. But the speed of light, which is a constant in the universe, right, is 300,000 kilometers per second. So we just have to multiply that 300,000 kilometers in 1 second. 1001. This photon that left here now, 1001 is now 300,000 kilometers away. You know, it's gone around the Earth several times in 1 second. You multiply that second times 60 for 1 minute. Then you multiply that minute times 60 for 1 hour. Then you multiply that hour times 24 for 1 day. And then you multiply that day times 365 for the year. And that's the distance of a light year. And it's the scale that is used for measuring distances between galaxies and celestial bodies. It's in light years, okay? So when we talk about 3 million light years away, that's a humongous distance, but it's a real actual distance of a number. It's not infinite, not infinite. It's very short of infinite, but it's an incredibly large scale. So you can imagine we've gone from nanoseconds, fractions of a second, to billions of years in those 2 moments of the universe, right? The inflation and the expansion. Yes, Hannah?
You mentioned the Hubble telescope. That's what they use to measure the galaxies?
Yes.
What about in other parts of the world, like Europe, for example?
Yes, so now there are a number of these telescopes that are orbiting the Earth, okay, and they're taking measurements. And typically now these collaborations, these instruments are so expensive, typically talk about billions. Sometimes they cost millions or billions of dollars to build them. So they're typically international efforts, like the International Space Station, right? It's a collaboration of several countries of the world, typically the most developed countries that have the budget for it. And so it's a collaborative effort. So these are international efforts. And when they get data, that data is pumped out to scientists throughout the world, 3, 4, 5, 10,000 scientists that are analyzing that data in different parts. Yeah, so these are really international efforts today, which is very exciting to see that going on. Okay, so this is just a little recap of the origin of the universe, origin and development of the universe, because I'm zeroing in on planet Earth, little by little, how our planet came about, okay? For the majority of that time, of that expansion, with the expansion comes a cooling, right? Because the original explosion was intensely hot, and it's what they call white hot, which is beyond red hot, to the point that it glows intensely, photons being emitted at a very high rate. Well, with the expansion also comes a gradual cooling of the matter. And with that cooling also comes a coalescing, a coming together because of gravitational pull. As this matter is cooled, also it is being coalesced. And at some point, these, let's take a star, which is a sun, all right? Our sun is a star. We have basically two types of objects on the universe that we can tell, the luminous objects and opaque objects, all right? So luminous objects is that they produce their own light, and typically they're stars. Opaque objects are going to be planets or meteorites or moons or smaller planets, but objects that don't produce their own light. In other words, they have cooled down enough that they're not emitting photons anymore. But stars, suns, are typically gas that is on fire. Our sun is mostly hydrogen. It's a huge ball of hydrogen gas that is on fire. It's been on fire for millions of years, and with any luck, it will continue for several more millions of years, but eventually it will run out, it will spend itself, all that gas will be burnt up, and then it will start collapsing. As it collapses, it also coalesces, and the atoms come together from the simplest atom of hydrogen, okay? It will start coalescing into helium, lithium, all the other elements that are more complicated atoms because of gravitational pull. And that process is called a nebula collapse. And they form these accretion disks. Okay, so accretion is another word for coming together or coalescing. So these disks are spinning. And as they spin, there is a balance of forces going on there. As they spin, there are centrifugal forces that are expelling matter, but there are also, as the matter is coalescing, especially at the center, at the nucleus, that is exerting greater and greater gravitational force. So there will also be a centripetal force, which is pulling in, all right? And planets end up in orbit by a balance of those two forces, of a centrifugal force. Whenever we spin something, it tends to fly out in a straight line, all right? But there has to be something else, some other force that is counteracting that force, that is perpendicular to the flying out motion, perpendicular at 90 degrees toward the center, if there is a center that is pulling in, and that would be the gravitational pull, which is a centripetal. It's called centripetal instead of centrifugal, right? So centrifugal is fuging, is a fugitive, is going out from the center. Centripetal is coming toward the center. So this balance of forces is what eventually will form the planetary systems. This accretion process will continue as these objects are cooling with the expansion of the universe that is continuing, right? And is cooling. So matter continues to collapse with itself, and it's a synergizing process. What do I mean by synergy? Synergy is something that perpetuates the activity, all right? And so what happens is, as matter, material matter, atoms, are collapsing and coming closer to each other and forming larger atoms, they themselves, because the density is becoming higher, greater density, that is exerting more gravitational pull, right? Which is one of the 4 fundamental forces in nature, the gravitational pull, gravity, and that attracts more matter yet. And as that more matter collapses in, that creates greater density, which generates greater gravitational pull and more pull. The thing with gravity is that gravity will lose its pull with distance. And so it's again, it's a question of how far the object is. If the object comes into range of the gravitational pull, it's going to be sucked in, and that object will collapse into the opaque body, which could be a planet or a moon, for example. And we look at the moon, and what does the moon have? The moon is all polka dot with craters, which are hits of asteroids and meteorites and stuff that has been flying around over millions of years, material matter. We should look like the moon, all like Swiss cheese. We're all polka like that. And why don't we? Because we have a very, very thin layer of a shield that is an extraordinarily hard shield in a way, all right? It seems like a very soft shield, the air, but this shield of atmosphere, which is incredibly thin, is protecting us from all the barrage of meteorites and comets that are flying constantly and would be striking Earth. Some actually get to penetrate through the atmosphere. They break up in the process. They go into fire because they have such speed. When they hit oxygen mostly and other gases in the atmosphere, they ignite and explode into fragments, which is a good thing for us. You know, and some of those fragments eventually make it all the way to land, and we have fine meteorites around. They're metals from space.
Is that what they call the meteorite shower?
Yes, exactly. When you see it,
Where
exactly.
did that occur?
Typically, one meteorite hits the atmosphere, the outer layer of the atmosphere. We'll devote one lecture to the atmosphere, and it breaks up into fragments, and those fragments light up they turn red hot or white hot, and that's what we see is the light, is the emission, the photons, and they continue to fragment, and thanks to that, they burn up literally in the atmosphere upon entry. So very spectacular stuff that is going on. Of course, the important factor here is time, a long time, typically millions of years, if not billions of years for all this to flow, okay? So it's a little similar to evolution. We're looking at the evolution of planetary systems, like our planet, our solar system with the 12 planets that we have. You thought there were 8, right? Okay, we'll get there. So from the accretion disk, which are collapsed stars, old stars, that this is called, typically they call this like a supernova, when it expands and burns and it goes from white hot to red hot, which is less hot, and eventually collapses due to gravitational pull. And then it explodes again like a secondary time, but because it's also turning on itself like a disk, it creates the accretion disk. And then individual matter will start coalescing and forming eventually the planets that will stay circulating around what is left of the original explosion, which is a single star, or what we call the sun. And this formation of planets from this nebula or huge, humongous cloud of burning gas to a planet, to a stable, more or less stable planetary system, which is what we have, is called the Planetesimal Hypothesis. Planetesimal, a reference to the formation of the planets orbiting around a sun that is relatively stable. In other words, we are, I forget if we're getting closer to the sun or further away from the sun, but it will take again a few billion years before we fly out into orbit or we collapse eventually into the sun, we meaning the Earth. And so we can consider it in our time scale definitely stable, because that will take millions, if not billions of years to happen. So you can see the combination of forces, the dynamic system of balance that needs to exist for these forces to show something that is stable, or to our time scale and to our size, it looks very stable. We look at night, we look at the sky and we see all the little dots, and we say, wow, everything looks in place and nothing is moving. Some are twinkling a little bit and twinkling, but it looks relatively stable. That's because our time scale is very, very tiny. If we speed it up, we'd see that that whole celestial sky is moving, right? The celestial dome that is called is moving from sunrise to sunset throughout the whole. You've seen those pictures from one horizon to the other. And even the little dots that we see, typically the little dots are not a single dot. It's not a sun, actually. They're so far away, so incredibly far away, that the little dots typically are a whole constellation. It's a whole galaxy with millions of suns that are so incredibly far away that they look like a single dot. Okay? It's like taking two flashlights and walking away at night, and at some point those two flashlights, those two little dots, those two lights start getting closer and closer to the sea. We see just a single dot, but it's still two flashlights. Okay, that's what happens typically with the little dots that we see, the little lights. And the big lights are typically planets that are reflecting the light, just like we see the light reflected from the moon. But they are opaque bodies that are reflecting the light of the sun. So they're typically Saturn or Venus, one of our neighboring planets. Okay, a little bit more about the solar system, our planetary system, our solar system. Okay, so this comes from the International Astronomical Union. Emma, you were asking, so there are these societies. This is one international society, the IAU, that looks at the planets and is the one that officially declares either a planet or a sun or a galaxy whenever it's discovered and names it. Typically now they get names with a combination of letters. It's like code letters and numbers that mean something to them. But so we have what is known as the 4 inner planets, or the small planets, and then we have the 4 outer planets, which are much larger. These are more or less to scale, but the orbits are not to scale, okay? But the sizes of the planets, yes. And then there are these 4 dwarf planets that we have discovered so far in our planetary system. I'm talking about the solar system of us, okay? Remember, we are one sun that is embedded in the Milky Way, the galaxy that has millions of suns. And we're one of those. We meaning the sun, our star. Okay, so the 4 inner planets, Mercury, Venus, Earth, and Mars. And here's our little moon. All right, as far as we know, the only one that has a moon of the 4 inner planets. Then there's an asteroid belt of debris that is flying out there, but it's not coalesced enough to form even a dwarf planet. But there is one dwarf planet that has been discovered already next to this asteroid belt. It's called Ceres. All right, so that's one of those 4 dwarf planets. It actually belongs to what is known as the inner orbits or the inner planets. After the asteroid belt, the distance gets much greater, much further away. We have the 4 outer planets that are known classically: Jupiter, Saturn, Uranus, and Neptune. But even, okay, and then Pluto, remember Pluto? Pluto has been downgraded to a dwarf planet. And apparently has its moon. And then there are 2 other dwarf planets. In other words, they are debris, they are material that has become large enough, has coalesced enough to qualify as a dwarf planet. And so the 2 others that are left are Makemake and Eris. And those are near, all these are near another belt of debris material that is out there that is known as the Kuiper belt. Kuiper belt. Okay. Sometimes they're named because of the scientist who discovers them. All right, so this is our planetary system. We got 4 inner planets, 4 outer planets, which are much larger, all in a relatively stable orbit around the sun, which is our star. And then we have these other dwarf planets that have been discovered so far, because they're too large to be a comet or an asteroid, and they are too small to be a full planet. So they're called dwarf planets, okay? As far as we know, there's no life in any of these. There may be some remnants of life, maybe in Mars, not really known, or at least water. It's known that many of these planets actually have water. Even the moon has water underneath the surface, okay, that it's frozen, which is the beginning of the possibility of organic life, right? Water, very exciting, but we need water at the right temperature for it to be liquid water, because no life in water vapor, that's very hot, and no life just in ice, that's crystallized, then you can't have metabolism because the molecules are kind of frozen together. All right, so this is just a review of our planetary system. Let's move on. Here, now the accretion also is for the formation of planets. So the accretion is not just for the formation of planetary systems, like the accretion disk. That accretion, which, like I say, it's a coalition, right? It's coalescing, it's coming together, occurs also at the level of planets, and that's how planets are formed. You can see here, the crust is beginning to form, but it's getting bombarded still by many asteroids that are comets that are being sucked in because of gravitational pull. It's a combination of gravity plus the actual trajectory of these rocks, these humongous rocks that could be the result of an explosion of some other planet or some other planetary system a few million years away, flying by. Eventually they get trapped, and there's a transition from white hot to red hot, and then eventually cool enough to have the magic molecule of life, which is liquid water, all right? And that liquid water has to be within a very narrow range of temperature, from 0 to 100 in the centigrade scale. This is an arbitrary temperature, right? Celsius, the Greek guy who invented it, or centigrade, we call it, because it's 100. It's simply a decimal system. It's a decimal system. We know that the Fahrenheit temperature, which is also arbitrary, it's a smaller scale, because what is 0 centigrade in Fahrenheit? What is freezing in Fahrenheit? 32 Fahrenheit, right? And what is boiling in Fahrenheit? Everybody remember? 212. So it's definitely not a decimal scale. Who knows what scale it is? I think it has to do with mercury. But you can see that the range is almost double. Because in the centigrade scale, we go from 0 to 100, right? The 100 single degrees. But in Fahrenheit, we go from 32 to 212. So it's almost twice as many, almost twice. So 1 degree centigrade approximately is going to be 2 degrees Fahrenheit, approximately. All right, when the accretion occurs, it's not a homogeneous accretion. In other words, the material that coalesces is also going to be reacting to gravity in a different way. It's going to be reacting to gravity by way of density. So generally, the most dense material will go to the core. And originally, the most dense material, which happens to be one of the most abundant materials in the universe, as far as astronomers can tell, is iron mixed with nickel, all right? And that forms the core. And then as more material coalesces in this accretion process and also cools, then there is a mantle that forms around the core. And that mantle is mostly molten rock. It's a mixture of many other elements on the table of elements, okay? But the core itself is mostly iron and some nickel. Then there's a second layer that we call the mantle, which is molten. In other words, it's liquid, but it's a thick liquid. It's a thick liquid, so it has its motion. And finally, when this cools enough, then the outer layer, the outermost layer of that molten lava will start solidifying, will become solid, which is what we call the crust of the Earth, the crust. Once we have the crust, it is cool enough to begin to have some liquid water. Because there's no possibility, there's water trapped in here, in the mantle, there's water trapped in the mantle, but it's water vapor, okay? And that water vapor actually gets released periodically onto the crust. But most of the water of the Earth, by the way, has been trapped. Think of a sponge that is originally dry, and you move that sponge through water vapor. What's going to happen to the sponge? It's going to get hydrated. It's going to start absorbing the vapor, the water vapor. Something similar has happened over the millions of years, whereby the Earth has captured water molecules. So most of the water on the Earth, the vast majority on the crust of the Earth, comes from outer space, comes from space that we've trapped by gravity, okay, or just by trajectory, which is fascinating. This theory was proposed in the 1970s, I think, thereabouts, because I remember hearing about it from one scientist, and everybody thought he was a kook, that he was totally cuckoo. And now it has been proven solidly that most of the water on Earth did come from outer space, from water vapor, water molecules that were floating around. So imagine how much water we've trapped, okay? It's amazing. And it is this liquid water that has made for the possibility of life on Earth, as we know it, organic life, and as far as we can tell so far, the only one so far that we know of in the universe. But we still have a lot to explore out there, an awful lot. Okay, let's move forward. I'm giving you probably too much detail, big things to remember, things like accretion, all right, the formation from the original, from the Big Bang, from nothing to something. And the two moments, the two big moments of that formation of the universe. First, the inflation, which is measured in fractions of a second, so incredibly fast, and then eventually transitions into expansion, and the scale changes to the opposite end, incredibly slow, to millions, if not billions of years, all right? To the total of just under 14 billion years, everything that we see in the universe. Then the coalescing of subatomic particles into subatomic particles, protons, electrons, and neutrons, and then those subatomic particles coalescing into atoms, atoms into molecules, and so on and so forth. And as that material, matter, continues to coalesce, it's exerting more gravitational pull and tends to pull more stuff inside, right? When we take that to the level of galaxies, what we'll end up with is planetary systems that are coalescing by this process of accretion. Now, let's move a little further here. Let's look at the Earth itself with its layers. Again, a little too much detail, but there are basically a couple of layers of each, so that the core, first of all, three main layers, right? The core, the mantle, and the crust. So three main layers for our Earth today: the core, the mantle, and the crust. The core is solid. The mantle is liquid, a thick liquid called molten. And then the crust is solid, basically solid, which is where we have the planets, and bigger than the planets, the continents, bigger than the continents is the plates, plate tectonics, that I'll talk about in a few minutes. So let's go back to the core for a moment. The core is white hot. And it's
how is it called? The liquid?
Molten, M-O-L-T-E-N, molten, which is lava, okay? That's where we get the word mantle from. Mantle comes from molten, M-O-L-T-E-N, molten. It's a thick, it's like dulce de leche. Yeah. All right, much hotter than dulce de leche. The core is white hot, and when we talk about white hot, we talk about 6,000 degrees centigrade. They're about 6,000, okay? Or 11,000 Fahrenheit, almost twice as much, right? Incredibly hot. So you know there's a simple little example of this. Remember the old luminescent bulbs? The luminescent bulbs, the bulbs that had a filament? All right, and sometimes you can get those balls that are transparent. In other words, they don't have the white fuzz on it, right? And you can see the little filament, it gets red hot and then it gets white hot. So that's when it starts emitting photons. That's before neons and before the LEDs and all that. But the good old luminescent bulbs, that's what happens. That little filament, there's so much electricity going through that filament that it turns white hot and it's emitting photons at that point. Just like the electrical stove is also emitting some photons, but it only gets red hot. And that's still pretty hot. You can get a big burn with that, right? But that's only red hot. White hot is super, super hot. All right, so from the core, which again is mostly iron and is solid and is exerting essentially the bulk of our gravity on Earth. Then we have the mantle around it, which is only 3,000 degrees Fahrenheit. In other words, half the temperature of the core, more or less, right? There's also an inner core and an outer core, not to worry too much. Then the mantle can also be subdivided into at least 2 layers, the lower mantle and the upper mantle, not to worry too much about that. But basically, the temperature and difference, you see, there's a lot of cooling that is happening in the mantle already. And that cooling is kind of counterintuitive, actually makes the mantle liquid in contrast to the core that is solid. But that has to do mostly with the elements that are there, because it has to do also with the gravitational pull that the iron atoms are exerting on each other that actually keeps it solid instead of liquid, right? But the liquid is the intermediate layer. It's a very thick, heavy liquid. And we see this liquid periodically when there is a volcanic eruption. That's the lava that eventually cools and forms more layers more on the crust, right? So the mantle is constantly layering on the crust. But the bottom part of the crust is also being dissolved away when it has an encounter with the mantle, and the lower crust, again, is being dissolved back into the molten liquid lava as there's a very gradual, slow process of cooling of the Earth. Again, over millions of years that we give off heat to the atmosphere, right? As part of entropy is energy that is lost, is the heat energy that the Earth is giving away simply by diffusion, by passive diffusion through the layers from the core to the mantle, and from the mantle out to the crust, and from the crust to the atmosphere, and from the atmosphere out to space. So that's the transfer of heat that is occurring on the Earth. Mm-hmm.
For the geysers, what part of the Earth is the water coming from?
Okay, that's very much at the crust of the Earth. It's very, very superficial, even though they shoot up very high. But that's at the crust, basically liquid water that by gravity, water is going to follow the pull of gravity, right? So if I pour this water here, it's not going to go up, it's going to go down because it's following the pull of gravity. Well, the same with the Earth. Water is constantly, in nature, finding its lower level, always lower level. That's how rivers flow out to the ocean eventually. And sometimes that water gets trapped into a crevice and will deviate back down into the crust of the Earth. And as it gets closer to the mantle, that liquid water will vaporize. Once it vaporizes, it's under pressure and it's going to shoot out. And so it's water vapor. It's liquid water that got vaporized with incredible heat. And now that water vapor is seeking to get out from the crust, and it's going to find whatever path it can find, and those are the geysers.
And the geysers only work in the summer, not in the winter?
It depends. It depends. They have their own cycles. I'm thinking of Yellowstone, right, which has very famous ones, and Old Faithful, which continues to I think they can time it. They put a time period on it. They can tell when it's going to erupt, that geyser. But yeah, it's a very fascinating phenomenon. But it's basically liquid water that is filtering down through the crust of the Earth until it gets close to the mantle, where it vaporizes. Once it vaporizes, it's like the cafetera, or when you're boiling water for the tea. Exactly. There's that. Exactly. You get that lava and go, and you get that shoot. Oh, that's like a tiny little geyser there. That's what it does. Mm-hmm. Yeah. Fascinating phenomena
And
are
like,
occurring
and
on
like,
Earth.
how do you call it, the water terminals, those areas where they have hot water?
Right? Okay.
How's that form?
Okay, we're going to get into that one, but that one is actually, that belongs to the hydrosphere talk lecture. But if we look at the Coriolis, so we have several currents to consider. We have convection currents to consider. We also have Coriolis effect, and all that is going to move the crust of the Earth back and forth, and that's what's causing the plate tectonics and the rubbing and continental drift. And those plates, tectonic plates that are rubbing against each other, that's what causes the volcanoes. And also the wrinkling into mountain ranges. So it's very fascinating, the whole geology of the crust of the Earth. Okay, let's move a little further and you'll see the stuff going on as we move here. How do we know about these layers? Because they're so deep, right? They're thousands of miles in, kilometers, miles. Here's a scale in kilometers. The core, let's see, 5,000 kilometers down, 5,000 kilometers, okay, so in miles, that's around, maybe around 3,000 miles, more or less, into the core of the Earth. That would be the radius of the Earth, 5,000 kilometers. No, sorry, that's only the core is 5,000. And then almost 3,000 for the outer core, so that's 8. And then the mantle, it doesn't give us a scale here. And the crust is only 100 kilometers thick, only. But anyway, how do we know about these layers? We know about the layers because of wave reflection and refraction, okay? Wave reflection and refraction of seismic waves, of earthquakes. So this is what happens. Two types of wave propagation. When a wave bends, a wave motion, right? Like my sound that is coming out of my mouth and hitting your ears, the waves of sound that are going through very fast, so we don't detect individual waves, we detect a composite. But my vocal cords are actually producing individual waves like a guitar, okay? And when the wave is bent, but maintains the same general trajectory, is called refracted. But when the wave is bent more than 90 degrees and it's coming back to the original trajectory, then it's called reflection. Like for example, the mirror, when I see the image on the mirror, that image is being reflected, okay? The image is being reflected. So it's a combination of these two types of wave propagation, either reflection or refraction from the epicenter of the earthquake. The epicenter is where the earthquake actually occurred on the crust of the Earth, and how it's picked up at different parts of the world, other points of the crust, at what time and at what intensity. So that's what they measure. Let's say it's an earthquake happening here now, which we're not in the seismic area, thank God. But let's say hypothetically that we would be at the epicenter, then where it's being picked up in New York, in Tokyo, in India, in Beijing, different parts of the world by seismologists. And again, there's a network of these geophysicists that measure both the time that it takes to get there and also the intensity by which that wave gets there. And they have been able to figure out which waves are reflecting and which are refracting. And that's how they have been able to determine, these geophysicists, what is the inner composition of the Earth underneath the crust, okay? It's by seismic wave reflection and refraction. So for example, when the waves hit the core, they're going to be reflected back out. But then when they go through the mantle, they're going to be refracted. They're going to be bent off the original trajectory. And you can see the actual data here, how it's collected and so forth. These little blurbs are seismic motions on seismographs, the little needle that moves like that. Okay, the seismograph. And this is meaningful. You can see from 0 minutes, 10 minutes, 20 minutes, 30 minutes, the propagation of the wave and how it's bending, how it's being picked up in different parts of the world. Anyway, so just to tell you how this, the mantle and the core of the Earth have been able to be figured out from while standing out here on the crust in a cool temperature compared to thousands of degrees. A little bit more detail about the composition and the thickness and so forth. Most of the interior is made up of the mantle, about 70%. Now this one is more to scale, where the core is down here, and then this is mantle, and the crust is just a very thin layer on top of solid that is cool enough for us to live so that we don't burn alive literally here, okay? And the difference in this crust to the mantle is in the thousands of degrees. So bottom line, the crust is an incredible insulator. It's a tremendous insulator of temperature. All right, let's look a little bit at the some of the physical forces that are moving the crust of the Earth. The main one being this convection currents that we have to understand, and this is part of what is known as fluid dynamics. Fluid dynamics, hydrodynamics, or aerodynamics, depending on where, oh good, this works on the
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct.
Okay, thank you very much.
Get ready for one of the most hypnotic things you'll ever see in a science class.
Wait a minute, stop. Sound. Okay, these are convection currents, all right? Convection current, like the word says, is a current. It's a current that is going to move clockwise and counterclockwise in opposition to each other, and they're going to generate a swirl, a current, but a current that is kind of roundish. It's going around and around and around. Okay, these are called convection currents. They occur in fluids, and fluids are liquids or gas. All right, it's a fluid. So obviously the water and the liquids are fluids. We're used to that, but we're not used to thinking of the atmosphere, the air, as a fluid, but it is a fluid. And for example, it's a simple little process. If I had a beaker full of CO2 gas, which looks whitish vapor, all right, CO2 gas, I could pour that CO2 gas out of the beaker and it will flow down like this. And that's what makes the Halloween scenes and all that, right? It's CO2 gas, because CO2 gas is thicker, is more dense than the air composition, than the atmospheric composition. And so it flows down to the lower point following the pull of gravity. And it's a gas. So I'm pouring CO2 gas into the atmosphere, into the air. Those are aerodynamics. So we have hydrodynamics when the fluid is a liquid, and we have aerodynamics when the fluid is a gas, like the atmosphere is a gas, okay? Okay, so these are convection currents illustrated in a liquid, in hydrodynamics. And they occur naturally. This is natural. It's a consequence of the movement of the Earth, the rotation of the Earth, also in combination with gravity. Here we go. So he's put different color stain.
Get ready for one of the most hypnotic things you'll ever see in a science class.
So he's put little stains.
Have you heard the
color.
heat rises? Well, here you can see it's true for yourself. I've got some food coloring on the bottom of a plastic container, and there's a hot mug right underneath the red food coloring. As it's heated, the water rises.
You can barely see the lip of the mug here, okay? You can see it better earlier. Hold on a second to explain what's happening here. Okay, so you see the mug here? I can see the mug, right? There are 3 mugs. This mug has hot water. And these two mugs on the side, they have no water. So there's a source of heat coming out of this mug. There's a source of heat that is hitting the plexiglass on the bottom, and it's heating up the water inside this chamber, this container. This container has water, and then he's put 3 dots of a stain, red stain here in the middle, right on top of the hot water mug, meaning right on top of the water that is going to get heated, right? It's not going to boil, but it's just going to, this water is getting heated by diffusion of heat from the mug through the plastic, the plexiglass into the water container. And then he put a blue dye here and a blue dye here on the sides that are not getting heated, so that one can see the motion.
Have you heard that heat rises? Well, here you can see it's true for yourself. I've got some food coloring on the bottom of a plastic container, and there's a hot mug right underneath the red food coloring. As it's heated, the water rises. But I want you to look closely and notice something else. The blue on the sides is being drawn in. You can see it better when I speed it up. Here's the thing I want you to remember. When water moves from one place, it doesn't leave a void behind. Water from somewhere else has to move in to take its place. That's why you can see the blue food coloring coming in from the sides. You can see it better from above. Watch that blue food coloring get drawn in. Do you see it?
Music's a little dramatic, but basically, yeah.
The hot water reaches the top, and then it gets pushed toward the edges by more hot water rising from underneath it.
Exactly, because it's not going to go out. It has to move through the surface.
As it goes out to the edges, it starts to get cool.
It cools.
And cool water sinks just as hot water rises.
It drops here.
And if you watch really carefully, you can see it sink and get drawn back toward the middle. These are called convection currents, and you see them moving here in 2 big ovals. They're one of the major things that drive ocean currents, especially in the deep oceans. But it's not hot water rising that drives the ocean currents. It's really cold water sinking up near the poles. Here's a piece of ice that I froze with some blue food coloring in it, so you can see how cold water sinks. As water sinks at the North Pole, for example, water has to flow up from southern regions to take its place. And these currents travel around the globe, some of them taking 1,000 years to complete their course. Understanding convection currents will help you get a grip on weather systems and the movement of Earth's continents over the eons, and even the workings of a lava lamp. If you want to try this for yourself, click on this link for all the directions you'll need. Thanks for watching.
Okay, so that's the convection currents. Is this clockwise and counterclockwise motion that will happen not only on the oceans, like you mentioned, but also the mantle is moving this way. So you can think of the mantle making these convection currents. When the mantle hits that crust, it's going to displace the crust to expand it away from each other on one part of the Earth, but also on another part of the Earth to bring crust against crust. And when those two crusts are buckling against each other, they're going to go up and form mountain ranges. All right, and so the mountain range is a wrinkling of the crust of the Earth as it's being pushed, as two tectonic plates are being pushed against each other like that over, again, thousands and hundreds of thousands of years. Yes. Yep. Mm-hmm.
Is it true that on the mountain peaks they have sea life, like fossils?
Fossils, yes. Again, because they came from the ocean that eventually was pushed against another plate, and then it was pushed up the mountains. And the interesting thing about For example, the Colorado, the Rocky Mountain Range, and many of the mountain ranges, the Alps in Europe and the Himalayas in Asia, is that you find marine fossils 1,000, 2,000 feet above sea level. How do they get there? Mostly because of this buckling up, right? Which is called uplifting. There's a name for it. So it gets us into this section here. I talked about the layers of the Earth. Now I'm going to talk a little bit about continental drift, convection currents, plate tectonics, and sea floor spreading. Okay, convection currents, plate tectonics, and sea floor spreading. Take a look at that for a moment. Go down on the presentation. Okay, so let's take a look at this slide for a moment. Here's the core, the bottom, the inner core, then the outer core, which is solid, right? Then we get into the mantle, which is liquid, thick, but liquid, which means that it is subject to convection currents. So these, what are called these mantle convection cells, right? Mantle convection cells, you see here, this would be like a pathway of heat coming up. And then when it hits the crust, underneath the crust, it has no more else to go. So it's going to move laterally under the crust of the Earth, under the crust, and it's going to push the crust laterally on both sides. And so there will be a line like we have the mid-Atlantic ridge, for example. I'll show you diagram of the ridge that we have in the middle of the Atlantic Ocean, North Atlantic, and then it goes down to the South Atlantic. And there, the ocean is being spread out to both ends, both east and west, by the pushing of the mantle from underneath. So the mantle, it comes to the crust, underneath the crust, and then it's going to push laterally by friction mostly. It's going to move that crust. At the same time, so there are several phenomena that are occurring here. We concentrate on that mid-Atlantic ridge, for example. We see the mantle rising. As it rises, periodically it's going to break through that ridge and it's going to deposit lava that is going to come out from the mantle, out through the ocean floor, and immediately solidify. When that molten lava hits the water of the ocean, which is an average of about, I think about 4 degrees centigrade, it's very cold water. Imagine the shock of molten lava hitting cold ocean water, right? Part of it vaporizes and it forms bubbles, and a lot of it is toxic gases that come out, and yet there is life that has managed to live in that area. These are the famous sea vents that have been found in Hawaii and other parts of the Pacific Ocean. Anyway, that lava that is coming out is being deposited on both sides of the ridge, and it's literally building up, crust is building up ocean floor that then gets spread out laterally, either toward the European side or toward the North American side in the Northern Hemisphere, or in the Southern Hemisphere, it's going to be either toward Africa or toward South America. So there's building up of sea floor, if you will, from the lava that is coming out. And that motion that is called sea floor spreading. So the ocean, the bottom of the ocean, what is known as the Benthic Region, is moving slowly but surely. It's moving very, very slowly, maybe 1 or 2 inches a year, which is really, when you speed that up, it's a lot of motion. And that floor is moving like this until it hits the continents. When it hits the continents, it's going to be wedged down, as for example here, and that crust is being wedged down because of another plate, another tectonic plate here of the continent. That wedging down, that crust, eventually when it goes far down enough, is going to melt, and it's going to remelt into the lava into the mantle way before it gets to the core, all right? Because the core is 6,000 degrees, it's gonna melt just about anything. No element can resist that temperature. So as this crust remelts, it reconstitutes the mantle. And there's a constant circulation of mantle that is happening, that is cooling, spreading, and then wedged back down into a molten state. And through the convection, that lava moves up again, cools, moves sideways, is wedged back down, melts again, and these are the convection currents. They're slow because the mantle is thick, but it's real because it's a liquid, all right? And all liquids are subject to convection currents. So the plates, as the plates move and are displaced, those are called plate tectonics. Tectonic is a term from geology that is the movement of plates, how continental plates are moving and rubbing against each other. On one side, they'll be forming mountains, mountain ranges, and on other sides, they'll be forming seafloor spreading. So here's a map that shows the major plates of Earth, and they all have names. For example, this huge one, the largest one is called the Pacific Plate. You can see it, all right? Then there's the North Atlantic Plate, which includes from Central America, North, Mexico, North America, Alaska, Canada, Greenland, that all forms part of the North Atlantic Plate. There's a Eurasian Plate that includes Europe and a good bit of Asia, mostly China, Russia. There are other plates, an Indian Plate here, okay? The Indian Plate used to be down in Antarctica and shoot off, and over millions of years migrated and slammed into Eurasia. And in that slamming, buckled it, and that formed the Himalayas, which is the largest mountain range in the world, okay? So that's the India subcontinent from the India Plate that smashed into Eurasia and started buckling it to form the Himalayas. Something similar happened here on the west coast of North America when the North American Plate and the Pacific Plate slammed into each other and started buckling up again. It created the huge mountain range known as the Rocky Mountains, which continues down into Mexico, Sierra Madre Occidental, all right? In the south, something similar with a Pacific subplate and the South American plate, again, slamming into each other, buckling up, and that generated the Andes. Mm-hmm. And so the major mountain ranges of the world, that's how they came about. Okay, so you can see what these plates are, and the little white arrows are arrowing their motion, in which way they're moving. That's also why the Pacific Rim, the whole Pacific coast and down into the Polynesian Islands and all this is called the Ring of Fire. Ever heard that term, the Ring of Fire? This is the Ring of Fire because this is all seismic activity. This is all volcano activity, all right? It's active sites all along. Imagine for Japan, Japan gets hit with earthquakes and tsunamis and hurricanes.
In Nicaragua, Father, is a very small country, and we have like 17 or 18 volcanoes.
Right, exactly. This is a very active seismic area, right, including some of the most spectacular volcanoes with what used to be, because it was uprising and it was like a saltwater lake that developed originally up there, trapped with saltwater fish, most of which with the rain, that salt water was turned into fresh water over hundreds of thousands of years, and most of the fish died because they didn't adapt. But some sharks adapted, and you have the freshwater sharks, which are some of the very aggressive sharks, and it's the one place in the world that has freshwater sharks.
Yeah, I don't know if there are still any alive, but we had.
Yes, yeah. So you think they've disappeared a little by little? They've been killed? And,
I think so because they have changed the,
yes.
you know,
El curso de los ríos, sí. The landscape, yes. Yes, a lot for agriculture and
They have,
Yeah.
we have a very delicious fish there,
yes, really?
and they have been putting in tilapias in
Oh
there.
yes,
So
Wipe
it's
them
called
out.
guapote.
Oh, yes,
The
guapote.
El
Guapote?
pescado, the fish that is in the Granada Lake.
Yes.
Oh my God, those fish are delicious.
Ah, yes.
They're getting extinct because the tilapia.
Tilapias, very aggressive. Yeah.
The other ones are not growing.
Thriving, yes, exactly. Yes, they're being replaced by the tilapia. Tilapia eats a lot, normally small, but if you feed it, it can get very large. Yeah. Okay, so here gives you a time scale starting 200 million years ago, a little over 200 million years ago. The theory is that we were one huge supercontinent that is called Pangaea. All right, Gaia or Gaia, that's the Greek word for Mother Earth. Okay, so Gaia or Gaia, Pangaea, one single mother continent that was clustered together like that. Like I said, a little over 200 million years ago. Fast forward about 50 million years, it starts breaking up. It starts fragmenting precisely because of the convection currents underneath, number one, and the continuous cooling on the Earth, number two. But guess what? 200 million years ago, we already had animals and plants living on Pangaea, all right? And they're gonna get separated into two major land masses. The northern part is called Laurasia. It's a reference to Asia, Laurasia. And the southern part is called Gondwana land, or simply just Gondwana. So Laurasia and Gondwana are the two major plates after the first fraction that occurs more or less equatorially, more or less at the equator. So you get a northern plate and a southern plate generally. The fragmentation continues into the precursors of the continents that we have today. For example, North America, Europe, and Asia continue to be more or less together still. Laurasia maintains more or less intactness, but the southern plate breaks up further into 4 or 5. You get South America breaking up from Africa. Then India also, imagine India was down here, like I said, and it slammed, it went north and slammed into Southeast Asia to form the Himalayas, right? And then this other plate that was Antarctica and Australia together, the precursors of Antarctica and Australia, right? You know that Antarctica is a continent in contrast to the North Pole, where it's just one big ice cube, block of ice, but no land underneath. Okay, so that's about 100 million years ago. Further fragmentation and movement of those plates to what we have today of the 7 to 8 continents, depending if you include India as a continent or a subcontinent. You got the North American plate, South American, Europe, Asia are still a single plate. Africa, it's its own plate. Antarctica separated from, or rather Australia separated from Antarctica. And then finally, like I say, India moved north and slammed into Southeast Asia at the bottom. Okay, so in 200 million years, all this evolution from one big supercontinent called Pangaea to 1, 2, 3, 4, 5, 6, 7, 8, even though Asia and Europe are still pretty much a single plate, are still together. The fragmentation. And you notice in general, it's a moving outward. It's a general motion out from this core. Let's say that this core, right? And these plates are fragmented, moving out from the center, from an epicenter, if you will, here. And it's projected that that movement will continue to move outward, but because we are in a sphere, as we move outward away from each other, eventually those plates would coalesce on the opposite side of the Earth to form a supercontinent, at the opposite side, heaven knows how many millions of years from now, with entire mountain ranges, new geologic formations that will come about then, in a few more 100 million years moving forward. And all this because the continents are really like rafts. They're like rafts that are floating on top of the mantle. And the mantle, because of convection current, is moving. And so we have a very interesting dynamic that is a slow dynamic, but very real. For example, this led to a lot of speciation because, like I said, 200 million years ago, we had all kinds of plants and animals on Earth, including the precursors to the dinosaurs and all that. And so when these plates fragmented and moved out, that's geographical isolation. So that makes for very good ground for speciation, to the point that today we have camels and dromedaries in Africa and Asia, and we have their relatives in South America, the llama, the vicuña, and the alpaca. Those are all relatives of the camels. They're all camelids. They're relatives of camels and dromedaries.
Yeah.
And they're divided by an entire
Australia,
ocean.
there is a Euro desert also. Estado de Coro,
Yes,
they have some similar species to the camels.
yes, that is endemic to that area. Yeah, you see? Yeah. Yeah, so geographical isolation is one of the major drivers of speciation. Okay, moving forward. Another way of saying the same thing. Here we have all the plates labeled, as you can see, and their motion, their relative motion to each other. So when they're moving away from each other, they're spreading. And you can see this one. I talk about the Mid-Atlantic Ridge. You see Africa here, you see Europe, then you see North America and South America, and in between is the Atlantic Ocean. And so it's a confluence of 1, 2, 3, 4 plates, and then if you add the Caribbean plate, little tiny Caribbean plate, 5. This Caribbean plate, by the way, is the one that caused that earthquake in Haiti a few years ago, and massive death, unfortunately. This little tiny Caribbean plate that is affecting all of Central America and the Caribbean. You have 5 plates coming together here, interacting with each other in the Mid-Atlantic Ridge, and by and large, they're moving away from each other. So there's a lot of seafloor spreading occurring in the Atlantic Ocean. In contrast with the Pacific, which is basically just one huge plate, not much spreading there, but rather the friction that is occurring on the edge, which is causing all that volcanic activity. The Ring of Fire is volcanically, seismically active. The whole coast of North America, South America, and then Polynesia and up Asia, all the way up to the Bering Straits with Russia. Okay, going forward. Whoop. Okay, coming close to the end here. This is a map. It's a National Geographic. I've always been fascinated by these maps where they take out the water and they show you the bottom of the ocean. Just amazing. Have you seen these maps before? Yes, you haven't? Oh, it's so interesting. This would be a physical map of the Earth, okay? In other words, you can see the bottom of the ocean. You can see the ridges. Look at this ridge here, all right? And they pretty much follow the plates. This is the Atlantic Ridge that I've been talking about. Mid-Atlantic Ridge goes right to the center. This mountain range here is humongous compared to the Rockies or to the Himalayas. For example, this is the Himalayas here, the largest mountain range in the world. This is the Indian subcontinent, right? This is the subplate of India here. So this is the Himalayas. Look at just the topography there compared to this type of topography that we can see. These mountain ranges here are huge, immense, compared to the largest mountain ranges that we have on Earth. Look at the Rockies, for example, the wrinkle here, all right? But that's all underneath the ocean. That's the ocean floor. The same that there are ridges and mountain ranges down there, there are also crevices and they called? Trenches, thank you. Trenches, you see, on the opposite side. So there's seafloor spreading occurring here, and that Pacific plate is moving north, west, so it's moving in this direction, and is getting sunk in these trenches here. In fact, the Marianas Trench is around here. It's the deepest part of the ocean. It's about 2 miles deep, I think. The Marianas Trench, which is on the opposite side of the ridge. So generally the seafloor spreading in the Pacific is in a, from the southeast to the northwest motion, generally, right? Very slowly but surely, this way, a few inches every year. In the Atlantic, by the way, the deepest area is just north of the coast of Puerto Rico, which is around here. It's called the Puerto Rico Trench. And that one is only about half depth, maybe 1 mile deep or something like that. That's the Puerto Rico Trench. It's the deepest part of the Atlantic Ocean. So you got Marianas Trench over here in the Marianas Islands, somewhere in Polynesian Islands. The deepest part of the Pacific, and then the Puerto Rico Trench, the deepest part of the Atlantic. But you can see here pushing over to the left, to the west, and getting sunk just before the Caribbean down. What saves us is that the North American plate is moving faster into the Pacific, and therefore we have a trailing edge. We don't have a leading edge, because the leading edge of the plate is going to be seismic activity. All right, it's going to be volcanic activity on the leading edge of the plate. But on the trailing edge of the plate, what we get is a long continental shelf. A long continental shelf of relatively shallow water, less than 200-meter depth. And that's the whole eastern coast of the US here, is a continental shelf that spreads out into the Atlantic. And so we don't have much seismic activity at all on the eastern seaboard of the US. In contrast with the western seaboard, where even just a few years ago, Mount St. Helens that exploded, it's volcanic activity. And the famous, that thing that's going through California, the fault, San Andreas fault. San Andreas, yeah. Okay, we have to move forward a little bit. I'm sorry, I have to push forward, but we still have the biomes to look at. So now we're going to concentrate on the life on Earth, finally, after all this geology. We're going to look at the biomes, and there are basically 9 biomes according to regions, general regions, all right? And they move from the equator north and south, from tropical to Arctic or Antarctic. But you notice, this is something else to notice, on Earth, here's the equator. And look at the land masses. There's much more land mass on the northern hemisphere than on the southern hemisphere of Earth, okay? In the southern hemisphere, we have basically this, about 2/3 of South America. Even Colombia, Venezuela, Peru, all that is in the northern hemisphere pretty much. Ecuador is right at the equator, right? But north of that, that's northern hemisphere. So just part of South America, part of Africa, the smaller part of Africa, because look at Africa on the northern hemisphere. And then some of the Polynesian islands, some of the Southeast Pacific islands, Australia for sure, New Zealand, Madagascar. But the rest of the Earth, of land, is north of the equator. Practically all of Asia, the bulk of Africa, certainly Europe, Central North America, Canada, Siberia, Greenland, all that landmass, the bulk of the landmass is in the northern hemisphere, okay? So that's where we would expect also the greatest variety of range of temperatures, and therefore habitats and variety of species, going from a tropical climate around the equator, north, eventually to the Arctic regions. So these biomes are the largest categories of ecosystems on Earth, biomes. And there are pretty much 9 of them. They line up, beginning with the tropical rainforest and the equivalent on grass, which is called savanna. So the savanna is typically also tropical, but no trees, all right, or very few. Then when there's no vegetation on the surface, then that's going to be the desert and the big desertification, mostly in Africa, but a few other spots also, Asia, Central Australia is one big desert. Then we get into the temperate region. Actually, here it's a little off. Temperate, we have temperate deciduous forest or temperate grassland, depending whether there's trees or not, all right? So temperate deciduous forest means that they drop their leaves yearly, annually, seasonally, and then grassland. And then we get into the northern regions that is going to be either coniferous forest or tundra. Tundra because it has permafrost underneath the ground and large roots cannot get there, so only shallow roots, which is going to be grasslands, but no major trees. All right, so these two, the coniferous forest, the pine tree forest, and the tundra are northern or very southern, like Chile, for example. And then the chaparral. Chaparral is a particular region that is mostly around the Mediterranean. That is scrub, small bushes and small trees, and has a very seasonal type of ecosystem. It's called chaparral, and it's mostly Europe, some of Turkey, Southeast Asia, and Northern Africa, around the Mediterranean mostly. Chaparral is a particular biome. It's very unique to the Mediterranean region. Let's see what else we got. Okay, then we have something called vertical zonation or vertical stratification. We can get a similar effect to the geographical spread from the tropical rainforest going north. Three major layers, if you will. We got the tropical, then we got the temperate, and then we got the northern Arctic region, right? If we go north geographically from the equator to the Arctic, we have tropical rainforest. Then we have the temperate region in between, most of US and Europe. And then we have the Arctic regions, colder and colder. We get a similar effect when we go from the ocean up a mountain or mountain range. So this one is vertical instead of horizontal. You follow me? Instead of geographically being horizontal from the equator to the pole, this effect, we get a similar effect if we go vertically on a mountain. This mountain could be in the middle of Central America, could be in the equator. And what happens is when we go high on the mountain, it's going to get into a tundra region. Similar as if we were in Alaska, but we're not in Alaska, we're in Central America, okay? And so we start at a tropical rainforest at sea level, then going up the mountain. This mountain range is in the equator region, all right? As we go up, the air gets thinner and colder. And so it's a temperature thing. The temperature makes the vegetation change. So we go from a tropical rainforest into a temperate region, and then we go into the coniferous forest, the pine tree forest, and eventually above what is known as the tree line. There's a tree line. Every mountain has, large mountain ranges, they have a tree line above which no more trees grow. Then we go into the tundra region. It's too cold for the trees and there's not enough soil, and typically the soil would be frozen. So the roots cannot go deep. So we get, this is called vertical stratification or vertical zonation that mimics the same as if we were to go from the tropics to the northern hemisphere to the pole, or south, either way. Interesting phenomena. And what drives this is mostly temperature. It's temperature, right? Okay. Finally, so this is an overview. I think there's a, oh, we still have the ecology book. Okay. I know I'm not going to be able to finish it by 12:45, but we'll go as far as we can. Okay, so to contrast here a little bit, the two maps that I'm showing, this one is the geophysical world, in other words, how Earth looks just on the nature of it. We got the continents, we have the ocean floor, okay? And these are the natural features, if you will. If we were to take out the water from the ocean, this is pretty much what a photograph would look like, where we have greenery, we have some browning because of the tundra regions. At the equator, we expect a darker green and so forth. And the ocean floor is going to be mostly a gray, brownish color. But this is the topography of the Earth in its natural state. This other one here is known as the geopolitical world. In other words, these are divisions by countries, The 190-something nations that we have in the world, about 196 or 98, something like that, just under 200 nations are represented in this map, okay? So here's the geophysical world, how it looks naturally, and this is what we've made of it by way of different nations and countries and so forth. The geopolitical world. Because this is where we live, in what nation, and how we are caring for that part of the territory. It's a very complicated situation, right? Okay, we're going to shift now a little bit into ecology, which is the study of life in community. Study of life in community, basically. It's a functional definition. Before I get into here, I need to ask any questions or comments from the other part. Talked a lot about the geology of the Earth. Probably went into too much detail there, but for setting the ground, some of the major issues is to have liquid water so that we can have life on Earth, and then the topography of it itself, and the various temperature ranges that occur. Now, let's get a little bit into ecology, which is the living organisms on Earth, the living organisms, all right? And so ecology is about the relationships, the complex relationships of the food web and things like this. How plants and animals and bacteria and fungi are related to each other in an organic whole that points to the biosphere. Bio meaning life, the life on Earth. Again, a life that we're talking about that is organic, that can be measured, and has been studied for many years. So we have the food chain, the food web, and the food pyramid. Then moving up from the individual, all right? Remember the hierarchy of life from the cell. We talked about the cell being the basic unit of life, all right? But most cells don't exist on their own. Typically, they come together to form tissues. Tissues where similar functions form organs. Organs with similar functions form systems or organ systems. And then systems with different functions are integrated into the organism. But we still have an individual organism, the 2 million species more or less that have been classified on Earth, the organisms, right? That make up all the species. Going beyond the organism, when we move beyond the individual organism, what do we have? The next layer is going to be a population. And then populations coming together form communities. Communities with the physical environment form ecosystems. And finally, several ecosystems together form the biomes or the biosphere. So we're going to look at these. Might not have time to look at them all today, but at least a little bit into the beginnings of ecology, okay? The study of life in community, the relationships on Earth. So, with regards to what is known as trophic relationships, trophic is a reference to food, all right? Trophic relationships, we have food chains, food webs, and food pyramids. And I can tell you that food chains are kind of hypothetical because they're very simplistic. It's just from one individual to, from one species to the next. But in reality, what we have in nature is more complex situation, and that's what we call food webs. But we start with a chain just by way of illustration. Just like we study, like in medicine, for example, you're going to study, will be whole courses devoted to each organ system of the body. But you know, if I laid out the dozen organ systems of the body here, laid out in front of us, we don't have an integrated body. We don't have a living organism. So those organ systems have to belong together in a complex whole, and that's going to be the web. So we start with a chain first so that we understand what's happening, and then we bump it up to the web level. And here we go. Here's a food chain, a simple food chain of 3 species. One species is a producer, and the other 2 are consumers. But one is a primary consumer, and the other one is a secondary consumer. So let's look at this. The plant is going to be the producer. Producer of what? Trigo. This is trigo. Yes, food, nourishment. Exactly. So this is wheat, all right? Has not ripened yet, but this is wheat. And because it's a trophic level, we're talking about food. So this is a food chain, okay? And food chain functionally means transfer of energy, because it is through our food that we get our energy. And we need energy for what? For metabolism. What's another way of saying metabolism? Staying alive, you know, like John Travolta. Okay, you remember, you're old enough to remember John Travolta. Me too. I know, the disco kid. All right, so we have wheat, plants. They're producers because they're producers of glucose, they're producers of starch, they're producers of food. And they do that through the process of photosynthesis, whereby they take light as a source of energy, and they transfer that light by the process of photosynthesis into chemical energy. And the chemical energy is the energy that is stored in glucose in the starch. When that glucose bond is broken, that chemical energy is released for metabolism. That other complementary process is what we call respiration, cellular respiration, the burning of glucose at the cell level, okay? So there's a transfer of energy here from sunlight to chemical energy, and then eventually from chemical energy to kinetic energy, to work energy, able to move, and motion after motion after motion after motion is what we call life, being alive. There's going to be a primary consumer that is going to feed on the plants. And that primary consumer is what we call a herbivore, because it feeds on herbs, on plant material. And that's the primary consumer. The mouse is a herbivore, many herbivores, okay, on the earth. They're animals. And they don't produce their own food, but they get their food from a producer. They get their food from plants. And that's why they're called primary consumers. They're not capable of photosynthesizing, but they're the first ones to reap the benefits of photosynthesis. Then you have secondary consumers that are going to feed on the herbivores, and those are going to be carnivores because they eat the meat, right? They don't feed directly on the plant. They feed on the herbivore, on the animal that feeds on the plant. And so they're secondary consumers or tertiary consumers. If someone else was eating the owl, then that other one would be also a carnivore, and that would be a tertiary consumer, because it's 2 steps removed from the original consumer, which is always a herbivore. So this is a simple food chain. We understand it, right? We get producers, the ones that photosynthesize. Then we get consumers, the ones that benefit on the production of that food. They don't photosynthesize, but they stay alive by way of the transfer of energy from light to chemical energy, eventually to work energy, which we know as kinetic energy. At the cellular level, that's what we call metabolism. All right, moving forward. Here is a more complex, a more realistic food web. You can see the layers of interaction. Always look for the producer first, because that's where the web is going to start, if you will, originate by the production of food. So in the web, at the producer level, you're always going to have plants. In other words, some kind of organism that is able to photosynthesize. But the photosynthesis will also help in producing other parts of the plant that are edible that will benefit the web. For example, nuts, seeds, and so forth. Seeds themselves don't photosynthesize, but they're a product of the photosynthesis of the plant. And then some birds, some animals are going to feed on those seeds specifically, on the fruit, all right, and benefit from that. Others may eat the roots, for example, the grubs. The roots themselves don't photosynthesize, but they belong to the tree, to the plant, and therefore they're benefiting from the photosynthesis of that consumer, okay? So you can see that the web is more complicated, but it's more realistic. It's really how life happens out there outside of this wall, on the other side of the window. Then moving beyond the producers, you're always going to have a layer of consumers, of primary consumers, that are going to be herbivores, rodents, birds, amphibians. The butterfly adult by way of nectar, but the butterfly caterpillar, remember, every caterpillar turns into a moth or a butterfly. The caterpillar is the juvenile, is the larval stage of the butterfly or the moth. And those caterpillars are incredibly voracious. They will eat 10, 20, 40 times their weight every day. Imagine if you all weigh 100 pounds, right? And you're going to eat 200 pounds of food every day. All right? It's insane. Or 1,000 pounds of food every day. It's insane. They're very voracious. The insects are very voracious, especially the larval stage, because they're preparing to do that transformation, that chrysalis, that metamorphosis into the adult stage, which they need very little. Just a little nectar here, a little nectar there, until they mate, and then they die. All right, more rodents and other large herbivores, the cattle and ruminants, right? They ruminate their cud, they chew the cud. They have secondary consumers, carnivores that are going to be feeding on these herbivores, right? And then you get tertiary consumers. These typically are known as top carnivores. The middle one is known as omnivores. You can tell typically from the teeth structure that they have. And some omnivores also eat plant material periodically, okay? But the carnivores eat strictly flesh. They're on a meat diet. And they typically hunt the meat. Different from fungi, for example, which are saprophytes. Saprophytes, you see it here on the side. Saprophytes are decomposers. These are fungi and bacteria, which are neither plants nor animals, but they're key to the food web because after all these guys are done eating each other and generating all the excrement plus their carcasses, somebody has to come and clean up the mess, literally. And those are going to be the bacteria and the fungi, because they're going to feed on carcass and feces and all that, and they are known as saprophytes. Sapro is dead. They feed on the dead, okay? And they are decomposers, and they are essential because they turn all these waste products and carcasses into nutrients, which are then reabsorbed by the plants. And that's the completion of the web there. Plants are going to absorb the nutrients that are the leftovers of all these decomposing material that is going on Earth. And thank God for the fungi bacteria, otherwise it would be buried miles of dead feces and carcasses over the millions of years of animals and plants that have died, right? So you can see it's a very complex and beautiful, very well organized, and these are niches. When there's an opening, some animals, some plants, some bacteria, some fungus is going to come to inhabit that niche, to take over that habitat, all right? And that's how nature works. Nature is very opportunistic that way. And it keeps the whole web alive, basically. Well, the pyramid, and I'll stop here with the pyramid. This is the last concept. For lecture today, I know I've given you a lot of stuff, but the pyramid is basically quantifying the web, okay? Quantifying the web, so we start at the bottom of the pyramid with the producers, with the plants, and then we move up the web into the primary consumers, secondary consumers, and eventually the top carnivores at the very top. This happens both on Earth, on land, and it happens in the water. So there's a food pyramid that happens on land, there's a food pyramid that happens in the oceans also, lakes, rivers, okay? The organisms differ, but the principles stay the same. The basic concepts are the same. Basically, the trophic level of the food pyramid is about a 10-to-1 ratio, approximately, for every level of the pyramid or every layer. That's why it's a pyramid. What I'm saying is that it takes 10 pounds of seal for a bear needs to eat 10 pounds of seal to put on 1 pound of weight. All right? 10-to-1. And a seal needs to eat 10 pounds of fish to put on 1 pound of seal weight, of seal meat. A fish needs to eat 10 pounds of plankton or krill to put on 1 pound of flesh. And the krill or the zooplankton needs to eat 10 pounds of phytoplankton or grass to put on 1 pound of zooplankton, all right? So it happens both on land and on water, and these are called trophic levels, and the ratio is about 10-to-1 approximately. Mm-hmm. And it happens in the Arctic regions, it happens in the temperate regions, it happens in the tropical regions. For a lion to put on 1 pound of flesh, it needs to eat 10 pounds of a giraffe or gazelle, right? And so forth. So that's approximate. That's the overall ratio. So you can see there's a lot of waste. It's a 9-to-1 waste. Because in order for me to put on 1 pound of trophy, I need to eat 10 pounds of chocolate or whatever the previous layer, okay? So that's a lot of waste. And it's functionally, it's energetically. So it's only a 10% profit, if you will, 10% use of the energy, of the chemical energy that is being passed from one layer to the other. And that's why it's definitely a pyramid, all right, and not the other way around, or not a cylinder either, because we're no way efficient. However, from that other 90%, other organisms, other creatures are feeding on that and are making good use of it. So nothing goes to waste in nature. All right, I'll stop there. That's enough. We'll get into the hierarchy of life. So forth. You can look at the slides, but I'll pick up here for next time. Okay. All right, well, I cover a lot, a little time, and this is a new area that we're going into. We'll bring in the human factor again on this later when we talk about populations, and we'll talk about some of the negative side, contamination, and then we'll talk about some of the positive side, creative things that are coming up to clean up our act on Earth, so that we may be able to coexist with the rest of nature and actually be good stewards like the Lord is asking us to be. Okay? Questions, comments? No? Everybody good? Yes, no? Mm-hmm.
I have statistics class on.
Yeah, okay.
On Tuesday.
So that's going to start, yeah, I think it starts next Tuesday, actually, yes. Tuesday.
It's not this
10?
Tuesday, the following, right? Because the summer actually
Right.
starts on the 11th.
You're right, yes, because next week is finals for this semester. So
Right.
we're anticipating, yeah, it's 2 weeks, 2 Tuesdays. Yeah, I think it's Tuesday 13 or something like
Right,
that.
after the Mother's Day.
Yes, right after Mother's Day. You're right, you're right. So let's put a date on it. 14, May 14. May 14, yes. So, oh yes, so we will not meet in person next Saturday, right? I'm going to send you the link to the video for next Saturday's lecture, which is only due until Wednesday, May 15, all right? But by that time, you would already have the first statistic class. And yes, because that's the day of ordination, yes, May 11th. So I'll send you that video. And then the following one, also May 18. There's no class, but I haven't scheduled any class for that one. So we have no class for that one, no. So our third session will be, yeah, you have a little break there, yeah, because also you'll have statistics beginning to pile up on you. So, yeah.
Well, I suppose that they're going to send us an email with the classroom.
Yes, yes, I think it's going to be the same classroom here. You know, it should be using the Zoom system and all that.
At 6.
Okay, 6 p.m. Yeah, 6 p.m. Okay, so, right, I need to send you that video, even though it's not due until a week from this Wednesday, but just for you to have it and you can look at it at your own pace. All right.
Father, how does for stats, what is the homework look like? Do we get problems?
It's going to be mostly problems, yes. Mm-hmm. It's going to be mostly problems, and she'll be teaching and video, so you can review the video. And then she also has some online resources for you. And I think that she's going to be devoting part of the class to going over some of the teaching material. But the first class, of course, has to be a review of the undergraduate part, the basic things, median, mean, mode, average, and standard deviation, and the basics of statistics first. And then she'll start getting more and more into the topic. Mm-hmm. Yeah. Okay, I don't know that much more about it because she's still designing the program, but she is aware that it's only all of you, all right? So it's tailored specifically for you. And I think she'll be drawing from some examples in population and in nature to use with statistics, like population growth curves and things like that, that will be relevant to the environmental course. So we'll try to work it that way, use examples from nature so that they're relevant to the environmental course also. All right?
And the course ends when, June?
Yes, it's the last week of June. It's the last week of June. So, for example, our class will be, the last one will be June 29. Yes. I'm not sure, we'd have to count eight weeks from May 11, yes. 8 weeks. So I don't know if it goes all the way to July 4 for the statistic. Let me see, for statistic, all right. 11, 18, 2, 25, 3, 4, 5, 6, 7. Yeah, see, I think July 2 would be the last class for statistics, July 2. Yeah. Okay. All right. Thanks again. I'm going to stop the recording now, which this time, thanks to God, I remembered. And here we go.